Alright, let's talk about one of those mind-bending quirks of thermodynamics, the Joule-Thomson effect. Imagine taking a gas and letting it expand through a valve, with no heat going in or out. What happens to the temperature? You might think, hey, it's just spreading out, maybe it stays the same? But no. For real gases, things get pretty interesting. Here's the deal. If you have an ideal gas, a perfect imaginary one with no attraction or repulsion between molecules, there's no temp change. Boring. But in the real world, gases have forces between their molecules. When you let a gas expand, those forces decide if things heat up or cool down. If attractive forces win out, the gas cools down as it expands. This is why nitrogen, oxygen, or carbon dioxide get cooler at room temperature when you let them expand. But for gases like hydrogen or helium, the opposite happens. They actually heat up. What's really wild is the Joule-Thomson coefficient, basically a number that tells you if a gas will cool or heat when it expands. Above a certain temperature, called the inversion temperature, some gases flip behavior. Below that, they cool. Above, they heat. And even though there's no heat exchange and the enthalpy stays the same, entropy actually increases. That's because when the gas expands, there are way more ways for those molecules to arrange themselves. More microstates, more disorder. Why does it matter? This effect is the secret sauce behind refrigeration cycles, making liquid nitrogen, cryogenics, and all sorts of cool science tech. So next time you see a frosty cloud from a gas tank, remember? It's all thanks to the wild world of molecular forces and a little thing called the Joule-Thomson effect.